is Newton's law of universal gravitation. And the second is satellite motion, which has really important roles, not in how planets orbit, but also for things like the International Space Station or weather satellites. Let's start with Newton's law. Isaac Newton, who was really brilliant, we've already studied his 3 laws of motion. He also was one of the co-developers of calculus, but he also came up with the rules that govern gravity in terms of classical mechanics. And what he figured out was that the force of gravity is directly proportional to the masses and inversely proportional to the square of the distance between the masses. He also understood this idea that forces are always an interaction between 2 masses. So gravitational force is an interaction between 2 masses. Okay? It looks something like this. The gravitational force is, well, if we do it with a proportionality, mass 1, mass 2 over r squared. Obviously, m1 and m2 are the masses, and r is this distance between them. So if we do a picture, here's m1, here's m2, and r is the distance from center to center. There has to be a constant of proportionality to get an equation. That took a little time, and it took a man named Henry Cavendish. Newton had maybe a rough ballpark idea of what that constant was, but he really couldn't measure that gravitational constant. It wasn't until actually about 100 years later that Henry Cavendish calculated it. So we now have a formula that looks like this. That's Newton's law of universal gravitation. And it's got lots of applications. It not only explains things like why apples fall to the earth, it also explains why the moon orbits the earth. Henry Cavendish calculated G, and G was equal to 6.674 times 10 to the negative 11. The units are so that this will come out in newtons, so we get a Newton meter squared per kilogram squared. It's a really small number, 6.674 times 10 to the negative 11. Because it's so small, gravitational forces tend to be very, very weak forces, unless, and it's big, one of these masses or both of these masses are really large. The only time we're aware of gravitational attraction is generally the attraction between other masses in the Earth that we're standing on. We don't notice gravitational attractions between everyday objects. It's an easy formula to just use. Let's just use it once. Suppose, for example, we have two masses. Mass 1 is 10 grams. Mass 2 is 0.500 kilograms. And they are separated by a distance of 5 centimeters. The one thing we're definitely going to have to do is make sure we always have units that are in kilograms, meters, seconds. That's an easy fix. So, mass 1, 10 grams, 0.0100 kilograms. I kept the 3 significant digits they gave us. And R, 5 centimeters, that would be 0.0500 meters. Again, I kept 3 significant digits. We'll put it in our formula. G is one of those numbers, the capital G. It's awkward, it's long. If you want to, and I think I'll do it right now, you can type it in your calculator and store it. 6.674 times 10 raised to the negative 11. And I'm going to just store that as alpha G. Where's my G? There it is. So now anytime I press alpha G, it gives me that number, and I don't have to type it in again. So this time I'll write it out one more time. 6.674 times 10 to the negative 11. Mass 1, mass 2, over the distance, squared. Don't forget to square the distance. It's an inverse square law. So that is alpha G times 0.01 times 0.5 divided by 0.05 squared. So these were pretty close together. They weren't really big, but the force between them is really tiny. 1.33 times 10 to the negative 10 newtons. One other important characteristic I'm not sure that I've mentioned is that gravitational forces are always attractive. Many forces can be repulsive also, like magnets and electrostatic forces, but gravity is always attractive. Now, on these two masses, they both feel the same amount of force. If we picture them, here's mass 1, it's fairly small. It feels a force this way. Here's mass 2, it's considerably bigger. I mean, we're talking about 500 grams compared to 10 grams. So 500's, considerably bigger than 10 grams. But they feel an equal force. They feel the exact same gravitational force, just in opposite directions. If that gravitational force was the only force acting on them, it would be the net force. One of the things you'll realize is, although they have equal forces, they'll have very different accelerations because of their very different masses. If we think about that, if that's the only force, let's find their acceleration. So if the net force is equal to mass 1 times its acceleration would be 1.33 times 10 to the negative 10 newtons divided by its mass of 0.01 kilograms. That's like multiplying by 100. So I get 1.33 times 10 to the negative 8 newtons. For the second one, I have the same force, but I have this much larger mass. Dividing by 0.5 is like multiplying by 2. It's going to actually come out to be 2.66. Oh, that was negative 10. Times 10 to the negative 10. Oops. These are accelerations. They're in meters per second squared. And you can see when we compare the two that the first mass, which was much smaller, has a much larger acceleration. It was 1/50th the size, so it has 50 times the acceleration. Which brings us to an idea I want to talk to a little bit more called proportional reasoning. One of the skills we want to be able to do in physics is understand how changing one variable affects the problem. Here's our basic. Suppose we have some gravitational force. And we want to know the effect of doubling both masses. I don't want to do the same ones in the notes because I want some variety. What happens if I double both masses? Well, the gravitational constant doesn't change, but this new mass is now twice as heavy as the original. This new mass is twice as heavy. The distance did not change. This comes out to be 4 times g, mass 1, mass 2, over r squared. What we notice is the new force is exactly 4 times stronger. So doubling both of the masses results in gravitational force 4 times stronger than the original. What would be the effect of doubling r? Well, we're not changing any of those, but if I double r, my distance is now 2r squared. Really important to realize that you're going to square that too. This is exactly 1/4 the original force. If you double the distance, you end up with 1/4 the original. We can do all kinds of things. Let's do one more. Let's triple M1 and triple R. Okay, we're going to have a lot of 3's in this problem. If I triple M1, leave M2 alone, and triple R, the numerator looks like 3 times G, M1, M2. And the denominator looks like 9r squared. Notice that's going to be 1/3 the original force. There's probably some questions like this on your Mastering Physics homework. There'll probably be a problem like this on the test. You need to be able to think, how does changing one variable change the force? Okay, let's talk about weight. If we are near the surface of Earth, we've been saying that the gravitational force, which is the exact same thing as the weight, is simply equal to mg. That's a lot easier than the law of universal gravitation. Why can it be so easy when we're near Earth, but if we want to get gravitational forces between anything else, we have to do this long, complicated formula? Well, if we're near Earth, we know the mass of one of the objects is in fact the mass of the Earth, and we know the distance between the object and the Earth is the radius of the Earth. So if you're standing near Earth, it looks like this. Radius of Earth, mass of the Earth. Sometimes I hear it's written as 5.98, sometimes I hear it written as 5.97, but give or take, that's the mass of the Earth. Okay. Let's look at the formula. The formula says that Newton gave us, looks like this. Well, one of the objects is mass of the Earth, the other objects we're just going to call M, the 2 kilogram mass or 1 kilogram mass, whatever it is. So there's G, M1, M2, and the distance between them is the radius of the Earth squared. Well, if we think for a minute, this is a constant, and this is a constant, and this is a constant. I can just calculate what all of that equals. And believe it or not, it's going to equal that. Now, they originally got this not by knowing all this information. In fact, we did not know what the mass of the Earth was until Cavendish came along and calculated G. But we did know what little g was, and we did know what the radius of the Earth was. That's how we calculated the mass of the Earth. Somebody had already calculated, I can show you that in a minute, somebody had already calculated that a 1 kilogram mass has a force of gravity of 9.80 newtons, and that the acceleration due to gravity was 9.8 meters per second squared. We'd already calculated all of that. Let me just stop and do a double check here. If I do alpha G times the mass of the Earth, 5.98 times 10 to the 24th, divided by the radius of the Earth, which I'm going to have to look up, it's 6.38 times 10 to the 6th, maybe. Let's double check. Yep, that's it, 6.38 times 10 to the 6th. So I'll put that in there. So I'm going to divide by 6.38 times 10 to the 6th. And double check that is in meters, yep. Squared. It comes out to be 9.80 times m. All of that every single time. So as long as we're sitting on the surface of the Earth, that's all we have to do. Now, if long as we're talking, let's back up for a minute and talk about Henry Cavendish. Henry Cavendish is credited with weighing the earth. There's a joke, his home, he was very wealthy, his home is still in England, and there was a little teeny shed where he did a lot of his scientific work out behind his big lavish home. And the joke is that's the little shed where Henry Cavendish weighed the earth. What he did is he took Newton's equation and he knew that a 1 kilogram mass had a force of gravity of 9.80 newtons. And he discovered G. Now, up until now, nobody knew the value of G, but Henry Cavendish measured G. He doesn't know the mass of the earth, but he knows this is a 1 kilogram mass. And other scientists had already determined that the radius of the earth was 6.38 times 10 to the 6th meters. All he did was solve this for the mass of the earth. The mass of the earth is going to be 9.80 times 6.38 times 10 to the 6th meters squared. I left off the square, don't do that. Divided by G, and of course 1 kilogram. I didn't write out G, but it's in my calculator. So if I take that and I work backwards, 9.80 times 6.38 times 10 to the 6th squared divided by G, and it comes out to be 5.98 times 10 to the 24th kilograms. So once somebody was able to calculate G, since we already knew the radius of the earth, it was very easy to actually calculate the mass of the earth. All right. What if we don't stay on the surface of the earth? That's when things get a little bit different. We know the behavior. We know that weight decreases as you move farther away. Remember, the gravity is inversely proportional to the distance squared. As we increase that distance, we know that the weight of an object is going to change. So let's think about how that looks. I just want to make a little table. I'm going to come up. Here's the distance. And here's R, O, and here's W. Let me change this to some, let me change this first column. The distance above the earth. Now, if you are not above the earth, you're on the surface of the earth, your value for R in this formula is just 1 earth radius, and we're going to call that a weight of W. So if you weigh W when you're sitting on the surface of the earth, that's that. If we go up a distance of about 100th of an earth radius. Now, 100th of an earth radius is about 40 miles, approximately. So if we're about 40 miles above the surface of the earth, that's only 100th of an earth radius. So this now becomes 1.01 RE. All I have to do to get my new weight is do 1 over 1.01 squared. If I do 1 divided by 1.01 squared, it comes out to be about 0.98. So this is going to have a weight of 0.98 W. So if you go up in the air 40 miles, you'll still weigh about 98% of your weight. You still weigh a lot. So when you're riding in airplanes and things, which don't fly that high, I don't believe, well, not typically. You weigh your weight. You're not going to notice a big difference. Now, if you were to go up 5/100ths of an Earth radius, that's about 200 miles. That's where the International Space Station is. It's about 200 miles, I believe. I should probably double check. But I believe that's where the International Space Station is. It's roughly 200 miles above the surface of the Earth. They call that low Earth orbit. This distance now has, and I should draw a picture. So this is just barely being above surface, and here's the International Space Station. It's out there a little farther. That's going to be 1.05 Earth radiuses. So if I do 1 over, I have to square that, 1 divided by 1.05 squared, they get about 91% of their weight. So those astronauts that look like they're weightless and they're bobbing around, they're not weightless at all. Gravity is still pulling on them, and that's really important. We'll talk about that when we talk about satellites. If Earth's gravity wasn't pulling on them, they're orbiting like this. They go flying off into outer space, and I assure you the astronauts on the International Space Station do not want to go flying out into outer space. The reason they appear weightless is because they're in free fall. And we're going to talk about that more when we talk about satellites in a minute. They're not really weightless. We call that apparent weightlessness. They appear to be weightless, but truthfully, they're just in free fall. So we can go up, let's go up pretty far now. So you think, well, that didn't do. What if you go all the way up where you're 1 full Earth radius above Earth? So here's 1 Earth radius, you're way out here. The distance, there's 1 Earth radius in the Earth, and you're up here at 1 Earth radius above the Earth. So we would have to use this. At this point, 1 over 2 squared root 1/4. If we double the distance, it's 1/4. If we triple the distance, you go 2 of these, it's going to be 1/9. I can write 1/9 as a fraction, but it'll be 1/9. If you were to go 3 Earth radiuses above the surface where your distance was 4 RE, you'd be 1/16 your weight. So yeah, somewhere around 3 Earth radiuses from the center or 2 Earth radiuses above the Earth, you only have about 10% of your weight. It gets really small. Obviously, by the time you get to the moon, which is 60 Earth radiuses away, 1 over 60 is 1/3600. When you're on the moon, the Earth's gravitational pull is pretty minimal on a person. So you will only notice your attraction towards the moon. The astronauts didn't feel the pull towards the Earth, they feel the pull towards the moon. However, because the moon is really big, there is a substantial gravitational pull between the moon and the Earth. All right. Let's talk a little bit about weight and gravity on another planet. at gravity on Mars. Now the radius of Mars is 3.38 times 10 to the 6th meters. So it's similar in size to Earth, but it's definitely smaller. And the mass of Mars is 6.42 times 10 to the 23rd kilograms. So you can see our radius is about almost double. We're almost 8 times bigger in size. Our mass is almost 10 times bigger. So we're, it's a substantially smaller planet. A substantially smaller planet probably has less gravity. Let's see what would happen. Suppose that they tell us that the weight of the Mars lander is 39,200 newtons on Earth. So we know what it weighs on Earth. And they want to know, well, what will it weigh when it gets to Mars? Well, we want to know the mass of it on Earth then. We know that weight equals mg. So if it weighs 39,200 newtons when it's sitting on planet Earth, that comes out to be a mass of exactly 4,000 kilograms. That's a helpful piece of information. Remember, mass does not change when you go to new planets. So in this case, if we want to calculate its weight is simply its gravitational attraction. So it's G, the mass of Mars, the mass of the lander, it's our second one, and then of course the distance between the two, well, that will be the radius of Mars when it's sitting on Mars. We put that all in, and we find out that it weighs 1.50, we have 3 significant digits, times 10 to the 4th newtons. On Earth, it weighed about 3.9 times 10 to the 4th. It's a lot lighter on Mars. Can we find the value of the acceleration due to gravity on Mars? What's g, little g, on Mars? Well, we know weight equals mg. So on Mars, it would be the weight on Mars divided by the mass on Mars. Well, the mass didn't ever change. And I get an acceleration due to gravity of 3.75 meters per second squared. That's a larger gravity than we have on the moon, which was about 1.62, but definitely a lot less than the 9.80 that we have on Earth. If we want to find how much it weighs farther above the surface of the Earth, let's do that. We've got the same Mars lander. It has a mass of 4,000 kilograms. But let's see if we can find the force of gravity 6.00 times 6 meters above Mars. We want to find that. What is the gravitational force going to equal if we go up that far above Mars? So let's draw a picture. So here's Mars. That's one Mars radius. But we're not going to do it from the right there. We want to come way up here and tack on an extra 6 times 10 to the 6. That's important stuff for them to know because when they get near Mars, it will be attractive. They have to be able to control those landings and things. So, how much does it weigh? It equals G, mass of Mars, mass of the lander. Only now the distance is much greater. Now the distance is this distance, 3.38 times 10 to the 6, plus this distance, 6 times 10 to the 6. And we have to do r squared. So our new distance between is the radius of Mars plus this extra distance above the Earth. Again, if we put all of that in a calculator, at that point, it's only going to weigh about 1,950 newtons, much less. That's probably, notice that it hasn't quite tripled the distance, but almost tripled the distance. So getting close to probably about 1/10 of the original force. Okay. Going to carry on. We're going to get through satellite motion. Satellite motion is basically really high-speed projectile motion. That may surprise you because let's think about it. One of the things that we know is that the Earth is a sphere. Not perfectly spherical, but it's curved. It's not a flat surface. And by the time something, if you look at the surface of the Earth, by the time you've traveled straight out this way, 8,000 meters, the surface of the Earth has dropped away a distance of 5 meters. That's not drawn to scale, obviously. So if you can fire something that goes about 8,000 meters per second, well, we know in 1 second it will drop 5 meters. It doesn't actually get any closer to the Earth. If you fire something horizontally at 8,000 meters per second, in 1 second it will have traveled 8,000 meters horizontally and it will drop 5 meters. This could be its path, and that could be the Earth. It doesn't actually get any closer to the Earth. Let me draw a different picture. So here's planet Earth, and you go build a really tall tower, really tall, a little bit bigger than a cliff. That looks pretty big, maybe not quite that big. And you fire a projectile, pretty fast, and it falls and it hits the ground. And you go, well, dang, it didn't go into orbit. So I'm going to shoot it a little faster. And it goes, still fell and hit the ground. But if I shoot it, here's my towel, my color it in. So, but if I shoot it even faster, I can go fast enough that it will orbit. Now, depending on how fast I do it, it may be slightly elliptical. I'll draw one that's not so perfect. Too slow and I get a bit of an ellipse. If I do it perfect, I get a circle. Or if I do it even a little faster, I get a bit of an ellipse. So not all orbits are perfect circles. We're going to primarily look at this idea of a perfectly circular orbit, which is usually what we want for satellite and things because they're maintaining a constant distance above the Earth. But like I say, if you here at 1 and 2, they're so slow they didn't orbit. 3 and 5, they made ellipses. They were either a little too slow or a little too fast. They did go into orbit, but not perfect circles. And then you have this sweet spot right here where you can get a perfectly circular orbit. Okay, for a satellite that's traveling in circular motion, the centripetal force, and this applies to the moon, and this is what Newton figured out, the centripetal force is gravity. Gravity, instead of having a tension in a string that's making that centripetal force, or a normal force, with gravity, you can have something in orbit, and it provides the centripetal force. So, for satellite motion, the centripetal force is equal to the gravitational force. That's really cool. Now, let's let our satellite have a mass of lowercase m, and let's the thing that it's orbiting could be a planet, it could be Earth, it can be anything we want. We'll call it big M. I don't know whether that's a planet or a moon, but it's something. How's this going to look? Well, the satellite's moving in a circle, so the centripetal force is mv squared over r. R would be the distance from the center, I'm going to go out here to 4, to the orbit. That's the orbital distance from the center of the planet to the orbit. The gravitational attraction between these two is capital G, mass of the planet, mass of the satellite, over this orbital radius. Well, right away we see one thing that's obvious is this speed does not actually depend on the mass of the satellite. We have a lowercase m on both sides, they'll cancel out. We also see that we are dividing by r here in the centripetal force. We're dividing by r squared here. So we can cancel out one of the r's. And we get this new formula that says that the speed of a satellite has to equal g times the mass of the planet or whatever's at the center over r. If you want to calculate, let's just stop. Let's calculate how fast the International Space Station has to be orbiting if it is, let me calculate real quick. I think I can do it. Oh, let me just ask my phone. How many meters above Earth is the ISS? Typo. Let's see. The average distance in miles, okay, it's about 400 kilometers above the Earth. So let's assume that 400 kilometers is right. Let's figure out how fast the International Space Station needs to orbit to stay in orbit. I also want to stop before we even do that. You know the centripetal force formula. You know the universal gravitation formula. It's really easy to connect those two. Okay. So, the ISS, International Space Station, is 400 kilometers above Earth. We know that the mass of the Earth is 5.98 times 10 to the 24 kilograms. And we know the Earth radius is 6.38 times 10 to the 6th meters. So let's draw that just one more time, just to be kind of careful. There's Earth. There's the radius of the Earth. And there's our extra 400 kilometers. There's the International Space Station. Now we gotta be careful, that is kilometers. So let's see what big R, then this orbital radius from here to here. It's 6.38 times 10 to the 6th plus 400 times 10 to the 3rd, 400 kilometers. So let's add and see how far from the center of the Earth it is. 6.38 times 10 to the 6th plus 400 times 10 to the 3rd, and we get 6.78 times 10 to the 6th meters. So this is our orbital radius here. That's what has to go in our formula. So we put it in our formula. I'm not going to write out G because I have G in my calculator saved. It's going to be G times the mass of the Earth make that bigger, divided by 6.78 times 10 to the 6th meters. So alpha G, oops, the wrong button, times 5.98 times 10 to the 24th divided by, now be sure when you're dividing by things like this that you're putting parentheses, so you're dividing by all of that, 6.78 times 10 to the 6th. If you don't put parentheses, you're going to end up dividing by 6.78 and multiplying by 10 to the 6th. So I get that, and then I just need to take the square root. And we find out that it has to be traveling at about 7,700 meters per second. Notice earlier I said it needed to be about 8,000, but it turns out as you get farther and farther, as this radius increases, then the actual speed of the satellite decreases. Notice the moon orbits us, but it doesn't have to go near as fast as the International Space Station would have to travel in order to orbit us. Okay, let's carry on. Let's do something else with those formulas. Let's erase all of this. We know that when something is orbiting, that the centripetal force is due to gravity. The centripetal force mv squared over r is equal to capital G, M, big M, for the planet or whatever it is, little m r squared. And we got something that said, we played around this, let's stop right here, that v squared is equal to, cancel out with the r, cancel out the m, g m over r. All right, remember when earlier we talked about, well, how fast is the speed of something moving in a circle? The speed of something moving in a circle was its circumference divided by its period, or 2 pi r over t. Let's put that in here. If I take this and I put it in there, I get something like this. 2 pi r over t squared equals g m over r. If I square this, I get 4 pi squared r squared over t squared equals g m over r. I'm going to solve this for t. If I solve this for t squared, I get t squared equals 4 pi r cubed over gm, or t equals the square root of all, I left off the square there, 4 pi squared 2 pi. If I take the square root of that, that's going to be 2 pi r to the 3/2 over the square root of gm. And you say, Miss Hughes, why in the world did you go to all that trouble? Really, I just wanted to show you one thing. That is Kepler's third law. Sometimes you see it written this way, sometimes you see it written this way. Notice that 4 is a constant, pi is a constant, g is a constant. The mass of the planet that you're orbiting is a constant. Like if we're thinking about orbits around the sun, then the mass of the sun would be a constant. And we see that the square of the period has to be directly proportional to the cube of the radius. Kepler figured that out not with universal gravitation. He figured it out from data. He figured out that t squared was proportional to r cubed for all of the planets that were orbiting about our sun. Newton used Kepler's third law to help him develop universal gravitation. But Kepler was pretty brilliant to come up with this before we had universal gravitation, strictly based on the data. And you'll see it written two ways. You'll see that t squared has to be proportional to r cubed, or you may see that the period has to be proportional to r to the 3/2. Those are equivalent statements. So we could write the law like this, or we could write the law like that. All right, let's work a problem. One more, and we're going to be finished with this chapter. We want to put a satellite in a circular orbit 300 kilometers above the Earth. We want a satellite in circular orbit 300 kilometers above the Earth. Let's see if we can find the speed, the period, and the acceleration. It's all all good things to find. I always start at the beginning on these problems. I know the centripetal force equals the gravitational force. mv squared over r equals g, big M, little m, over r squared. And then I go, oh, that's right, the mass of the satellite's not important. And one of the r's cancels out. And the speed of the satellite will just be the square root of gm over r. We already had found that previously, but it's just good practice to work through. Now for Earth, that's going to be the radius of the Earth plus 300 kilometers. 300 times 10 to the third meters. So I just have to solve for r. G's in my calculator. The mass of the Earth, I should probably put it in my calculator. I've used it so many times today. 5.98 times 10 to the fourth, that's the mass of the Earth, because we're going around the Earth. And this distance is the radius of the Earth plus 300,000 meters, or 300 kilometers above the surface of the Earth. Now it's just a really careful calculator punch. Let's see. Alpha G times the mass of the Earth, 5.98 times 10 to the 24th, divided by, and then I have this value for r, I have to add those two together, 6.38 times 10 to the 6th, plus 300 times 10 to the 3rd, and then I have to take a square root of all of that. Comes out to be 7730. I don't know if we have that many significant digits, but let's assume that we have 3. If I have 3 significant digits, that's the speed. What else do they want to know? They want to know the period. Well, think about how we can get period. We know that the speed is the circumference divided by the period, which means the period is the circumference divided by the speed. Oh, well, I have these numbers. If I'm going to go ahead and remember, r is going to be the radius of the Earth plus 300. The radius of the Earth, 6.38 times 10 to the 6th, plus 300 kilometers, so 300 times 10 to the 3rd. So my radius is 6.68 times 10 to the 6th. That's the orbital radius. That's this total distance from the center of the Earth all the way out to 300,000 meters above the Earth, divided by, and I'm not going to use my rounded, well, it was pretty close, 7729.6. Let's see, 2 pi times 6.68 times 10 raised to the 6th power divided by 7729.6. Comes out to be 5430, almost exactly. That's in seconds. If I divide that by 36, let's just divide it by 60. If I divide it by 60, it comes out to be about 90.5 minutes. Remember, that's about the speed of the International Space Station. And the International Space Station makes a trip around the Earth every 90 minutes. I don't know if you've heard that. So our numbers are making perfect sense. Now, If we get much, much further away and this gets much, much larger, like at the moon, well, then all of a sudden our period's going to be much longer, like 28 days long or 30 days long. I'm not sure. One more thing we haven't found, they want to know the acceleration. So we found the speed, we found the period. Acceleration is just centripetal acceleration. It's v squared over r. 7729.6 squared. The radius was 6.68 times 10 to the 6th meters. Let's see what happens if we do v squared over r. 6.68 times 10 to the 6th. 8.94 meters per second squared. Oh, that seems really reasonable. The acceleration on the surface of the Earth is 9.8. This is about 91% of the acceleration. We're 300 kilometers above the surface of the Earth. That's right in line with our other problems. Okay, that concludes everything I'm covering out of chapter 6. There's a little more information in the notes if you're interested in reading about black holes or how they use some of this information to determine the mass of other planets. We simply don't have time for everything we would love to cover. If we met 5 days a week, you know, if this was a 6-hour course, we might have time, but we don't. So that's all of chapter 6.